Hi, how are you? Um, I decided to make a video out of this answer, give you a video answer because there's quite a bit of graphics that can be explained here, and it's easier to explain using a little bit of diagrams. Okay, while when you're using just answer um, form may not be very you know easy to understand. So, but this is will be much better represented if I do it in a video. Okay, so here you've got a spring and you've got a mass attached to it. That mass is given to you as how much is that mass? 0.256 256 grams. So the mass is 256 grams, and you could convert that immediately to kilograms. It will be 0.256 kilogram. Okay. Now, after you attach this mass, you are outstretching the spring by a distance of. So this is your position one of the spring. Okay. And this at this point we call this your equilibrium condition here. Equilibrium. So after you outstretch the spring a certain distance, well, in this case, let me draw. When you outstretch the spring, say this like that. With the mass on it, you outstretch that spring by a distance of 18.2 centimeter. So I'm going to draw. Excuse my graphics here a little bit shady. There you go. So this distance here, you outstretch the spring that distance 18.2 centimeter, which is so this is your distance d that you outstretch the spring for is 18.2 centimeter, and I want to change that to meter immediately. So divided by 100, I get 0.182 meter. So that distance d here is your 0.182 meter that you outstretched from this position 1 to position 2. Something like that. Just want to make this visibly clear what we're trying to do. So this is your equilibrium point right here. Okay. So, and you're asked to find the spring constant, which is K. Okay. K, the spring constant, since we're working with kilogram, meter, it will be a force divided by force will be divided by, say, distance x, such that this will be your Hooke's law that will say F equal to kx. So, which means that this K that we're looking after is going to be in Newton per meter, because force is in Newton and x is in distance in meters. So this, we call that K the spring constant. We can also call it the stiffness of the spring. So both terms will be fine. And if you want to call it spring constant, it's fine. You can also call it the stiffness of the spring is in Newton per meter. So how do we find this K? Well, we have to look at the two positions that you got here. First, you got this initial position, and second, you got this final position. Now, in the final position, let's just call that position 2, okay? When you have outstretched spring to this point, your velocity that you're at this point is 0, right? So V at position 2, 0. I can also call that V final, okay, is 0 right here. So what does that help me to do? Well, we can use the principle of conservation of energy to solve this, okay? So what does the principle of conservation energy say? Well, it says that the potential energy, call it potential energy at position 2, okay, is equal to 1/2 the mass times the V, and in this case it's the V final squared, plus 1/2 of what? Well, when you had pulled this spring up to here, the potential energy at this point is going to be the kinetic energy that wants to, at this point, the kinetic energy at this point is 0 because the V final is 0, so that goes to 0. Okay. Plus, whatever the spring wants to pull back into here, the spring wants to pull back an energy of 1/2 times K, which is the spring constant, times D times the distance squared. Okay, so that D distance squared is your how much energy wants the spring to pull back to come to this position. Okay, now in position 1, when you've reached this point, the spring is not going to be 0 here. The spring is going to continue to another position, and the mass m here. And this distance here is not what we're concerned with. What we're saying is that when you have released the spring is gonna go back up. It's gonna pass through the equilibrium position at a velocity. Okay, so that velocity is V initial. Okay, and it will continue until it reaches in section 3. Well, I'm sorry, position 3, a point where it's here, where the velocity reaches again 0. V final in this position 0. But we're not concerned with what's happening at position 3. We're concerned what's happening right here at the equilibrium point. Well, at the equilibrium point, what is the potential energy? First, what do we know? We know that V initial is given to you in the problem as 0.746 meter per second. Okay, and we know that the potential energy at position 1 is going to be 1/2 m V initial squared plus 1/2 K D squared, right? So at position 1, D is equal to 0 because you've reached equilibrium point. So you outstretched at D, then you let this go. It went back to the point where it's 0 here. So in this case, D is equal to 0. And guess what? This term goes to 0. So you now we apply the law of conservation of energy, which is law of conservation of energy, which says that the potential energy at 1 should equal to the potential energy at 2. That is the law of conservation of energy. So we're basically equating these two terms together. So will be half k d squared equal to half the mass times vi squared. And you can see here half and half cancel out. And what are we solving for? We're solving for k. So k simply is this value divided by d squared. So m vi squared divided by d squared. So let's apply some numbers. The mass is given to us at 0.256 kilogram. So 0.256 kilogram times initial velocity is 0.746 meter per second. So 0.746 meter per second, but that is squared. So we're going to square that. All of that divided by d squared. D squared is the distance given as 1.182 meter, and we're going to square that. So 0.182 meter, and we're going to square this. So we're going to work the numbers and we're going to work the units, and we should arrive at a stiffness units of Newton per meter. If we don't, then there's something is not right. Okay. So if we multiply all of that, I did that already, you will get 4.3. Okay, that's in numbers. Now what's happening with the units? You get kilogram times meter squared per second squared divided by meter squared, right? Meter squared and meter squared canceled out. So you will get k equal to 4.3 kilogram per second squared. And then we're going to ask yourself, well, how is that going to be Newton per meter? Well, we're going to remember something here, that what is the Newton? So how is that going to be? This should be, the K should be in Newton per meter. So does kilogram per second squared equal Newton per meter? Well, let's resolve Newton per meter. Newton is kilogram meter per second squared. Okay. And where's that coming from? Mass times acceleration. So to get the force in Newton, it's kilogram times meter per second squared divided by meter. So meter and meter cancel out, and you get kilogram per second squared. So Newton per meter is also equal to kilogram per second squared. And this is the stiffness of the spring. And the stiffness of the spring, or the spring constant, is 4.3 Newton per meter, or kilogram per second squared. Let me check quickly something and we'll close out this video. Okay, I checked the calculations. The calculation seems to be accurate. Anyway, this is a solution for this problem, and hopefully you will be able to solve problems similar to that when you basically understand this theory of potential energy. Take care.